All right, welcome everyone. All right, thank you. Thanks so much for being here today. We are so excited to have you and to have this great lineup of speakers. We're especially grateful to those who have traveled from out of town to be here. This is part of an initiative of the Wisconsin Energy Institute for building a circular bioeconomy ecosystem in Wisconsin and the Midwest, the aim of which is to help share knowledge and to build connections among stakeholders in the bioeconomy. This whole effort is funded by Innovation Incubator, which is a collaboration of Wells Fargo and the National Renewable Energy Lab. They are specifically interested in energy and agricultural innovations. They run an accelerator program, and they also are interested in innovation ecosystems overall and have built a network of collaborators across the country. And we're very grateful to them for their support. I'd also like to thank the promotional partners who help get the word out about these events. In addition to those in the room, we had about 160 other people who have signed up and who are participating online. So from across many different states and even internationally. So it's exciting that so many people are interested in this topic. This is part of a first phase of this initiative. This is a third of 3 workshops. The first was on renewable natural gas, the second on carbon management, and now today's workshop on sustainable aviation fuels and bio-based chemicals. The next phase will be setting up 2 more conferences this spring. The dates are still to be determined, and we'll be discussing the workshop findings, exploring these topics further, and then also considering ongoing strategies for how we keep this effort going. So thanks again for joining us. I did want to just quickly introduce the support team for here today. In addition to myself, Allison Bender and Scott Williams from the Wisconsin Energy Institute are here. Deb Gerke and Steve Bialak from the Madison Office of Strategic Consulting are also here as well. So next, I'll leave it there. Next, I wanted to introduce Dr. Tim Donohue, who is the director of the Wisconsin Energy Institute and the Great Lakes Bioenergy Research Center. He is the Ira L. Baldwin Professor of Bacteriology and UW Foundation Fetzer Bascom Professor at the University of Wisconsin-Madison. He's an internationally recognized expert on bio and genome-based conversion of renewable resources into valuable products. And he's been very involved and is the past president and current secretary of the American Society for Microbiology. So welcome, Tim. Thanks for being here.
Well, thank you, Mary. And thanks to Mary, the team, and all the speakers for being here on what I think is going to be a very exciting day in a lovely February day in the state of Wisconsin. Blue skies. My job in the opening 10 minutes is to give you all a 50,000 feet above sea level, no pun intended given the topic, view of what goes on in WEI and try to set the stage and the topic and the challenges that we're all working together to solve in this space. So if I move forward to the next slide, let me just tell you what I think WEI is doing to contribute with all of you from industry and other universities that are with us in person and online to help solve one of the greatest challenges facing society as we roll into the 21st century. WEI is a cross-disciplinary, cross-campus research institute, about a block and a half that way. We have programs that are set up to catalyze moving the university and the state and the country and the world forward in energy. That's our tagline. And that includes programs in the stationary sector, which we're not going to talk about today, on more efficient energy capture, storage, and distribution systems, so-called smart grids, and battery research. We also have programs and major programs in the transportation and products field that we will spend a lot of time talking about today, including making renewable fuels, vehicles, and more efficient engines. And in the product space, something we won't talk about today is direct air capture of CO2 and being able to use it to make carbonates that harden cement as a way of bypassing the need for petrochemicals to do that. That's one renewable material. We will spend more time today talking about renewable fuels and renewable chemicals and materials from agricultural residues in particular. So let me give you my view of the circular economy and its role in society. I don't expect you to read everything on this slide, and I'm not going to go through it. But on the left in blue, some, I think, very important examples in Wisconsin and other states in the United States of today's industry. And in the box on the right in green are what we vision as industries of tomorrow who are using bio-based substitute to make new products listed down there from all of the things in the blue box on the left. And we at the University of Wisconsin and the Energy Institute have research programs that sit in the box in the middle to enable this transition of today's industries to industries of tomorrow. And this includes field, laboratory, and computational work to make new processes that tomorrow's industries can depend on to produce these materials in a sustainable and cost-effective way. And it includes both physical sciences and biological sciences approaches. So I want to make it clear again that this is interdisciplinary. So we envision a future that the landscape of a state like Wisconsin will look something like this. It'll have renewable sources of energy and things that are already relatively mature, but still getting better in wind farms and solar, hydro. But over on the left, we envision a whole new type of biorefinery that can make a myriad of fuels and chemicals that we currently get from a petrochemical refinery. And to give you an example and toot our horn a little, I want to take 1 or 2 minutes to describe a signature program on the UW Madison campus that sits in this lower left-hand quadrant that allows us to think about what would go on inside that biorefinery, what would come in, what would go on inside, and what would come out. And that's something called Great Lakes Bioenergy, which is one of 4 Department of Energy funded bioenergy research centers in the United States. We are in our 16th year of existence with DOE funding. And our mission is to develop the knowledge to take energy crops that are grown as sources of fuels and chemicals, figure out how to convert them into those types of products. And you'll notice on this slide, those energy crops are not grown in agricultural space. They're not grown on food grade land. So these are specific crops grown in specific acreage that would be separate from food production. So it would be able to grow the use of agricultural residues for this purpose. This is an example at a very high level of what our platform looks like. Moving from left to right, we are evaluating and developing new types of crops that can be used as energy crops as a source of the renewable carbon that will be able to be converted into fuels and chemicals. We have developed technologies to separate those lignocellulosic fractions of those crops into the major polymers, the polysaccharides on the top, and the lignin polymers on the bottom. And we have developed methods to deconstruct that into their monomeric or water-soluble units that we can then feed to specially engineered microbes and microbial communities to make either fuels on the top from the sugars or chemicals on the bottom from the aromatics. So in just a couple of words, the fuel that we're focused on is an industry-ready fuel, isobutanol, that can be used for aviation, that can be used for diesel, and that can be used for gasoline to replace the parts of those fuels that come from fossil fuels. The chemicals on the bottom that we are focused on and making from aromatics are several compounds that industry is waiting for to make bio-based precursors for nylons, polyesters, and other materials that they currently depend on petroleum as a source of those materials. So we see this biorefinery as one that makes fuels and chemicals from a ton of biomass that shows up at the local loading dock gate. And in that way, if you look at the green barrel on the right, that refinery would work very much like a petrochemical refinery. Inside of that green barrel is how a petrochemical refinery makes its money. They make about 50% of their money by making gasoline, diesel, and jet fuel. That's the large volume, low profit product. They make about 50% of their money from making tens of thousands of chemicals from that little yellow slice on the top. So the chemicals are the high profit, low volume commodity. And in fact, it's the chemicals and the profit from the chemicals that keeps the price of the fuel, don't throw something at me, as low as it is today, okay? And so we've already demonstrated this, and Dan Nagira this afternoon will give you some examples of the chemicals that we're making from the non-sugar part of the lignocellulosic biomass. And if you do a TEA of that process, it shows there are both environmental and economic advantages of making products from all major parts of energy crops, so that these biorefineries will work like petroleum refineries. So my last slide here is just come back to the theme. We're all about energizing the Wisconsin idea. For those of you who aren't from UW-Madison, the Wisconsin idea is in our DNA. It says that the university is here to provide knowledge that improves the life of the people of the state and the world. And this circular bioeconomy is a way to get there. Done right, it can lower net greenhouse gas emissions. It can upcycle the abundant raw materials that are on the left part of this slide. We believe the data is showing that we can deliver cost competitive products. And by siting these refineries close to where those ag residues are made, we will be delivering economic opportunity to underserved regions and people in the United States and help them participate in what is currently a multi-trillion-dollar per year industry. So with that, I think I'll stop and pass the microphone off to Deb and wish you a good day. And if anyone wants to talk to me, please call me at one of the breaks. Thank you.
Thanks, Tim. You can just leave it on. Well, I'm already blown away, but then I'm easy because I don't understand any of this stuff. So welcome. My name's Deb Gerke. I'm from the Office of Strategic Consulting, and I'll be the person moderating and sort of moving us along throughout the day. What we're going to do today, we're going to have an overview of sustainable aviation fuels and then an overview of bio-based chemicals. Then we'll have a little brief discussion about it, because one of the reasons we brought you all here today is because we want to know what you all think, what you all need, how to work with the Wisconsin Energy Institute to better move along these projects, remove any barriers so that we can be successful at moving towards that sustainable future. Then we'll take a break because that will be a lot of work for the part of the morning. And then when we come back, we will hear about policy regulatory overview for sustainable aviation fuels, and then the same for the bio-based chemicals. Then we'll hear about some case studies from each of those. Then we'll have lunch, which is always the highlight of the day. Then we'll have some more case studies, breaks, and wrap up with a discussion of where we go from here. And it will be the end of the day. You might be tired and you might be tempted to leave, but we really hope you stay to the end. Again, part of the reason we're here today is to learn what you all need and what you're thinking about this work. And so we can't do that if you're not in the conversation. So we hope you stay for the end there. If you needed to use the restrooms, they're right outside this door. Go straight back to the other wall. You'll see a big red wall on the left, and that's where you'll find those. And we're going to start by just taking part of the reason people come to these things. Oh, and I need to mention, we do have some folks on Zoom. So we have roomies and we have Zoomies. So we have to pay attention to those folks back there as well. We just want to take a minute. Part of the reason you come is to network. So just turn to somebody at your table and just, introduce yourself if you don't know them, and maybe explain what your interest was in attending today. Just take a brief minute. You may have already done that, but. You're the first speaker. I'm guessing you just say your last name, Csonka?
Yes, ma'am.
Okay, good.
I'm on. I'm ready to go.
Okay. You'll have more chance to talk during the breaks and lunch later. Just wanted to kind of get us warmed up. So we're going to get started with our first speaker, who is going to provide a technical policy and market overview regarding sustainable aviation fuels. And for this, I'm going to have to put my glasses on because I'm going to have to do quite a bit of reading here. So Steve Csonka is the Executive Director of the Commercial Aviation Alternative Fuels Initiative, which is a coalition of airlines, manufacturers, energy producers, researchers, and government agencies working to develop and deploy alternative jet fuels for commercial aviation. With more than 35 years of experience with commercial aircraft engines and fuels, he holds a master's degree in propulsion and combustion engineering for the University of Cincinnati. Go Bearcats.
Thank you. Go Bearcats, go Bengals. I go back to being a Salukee too, way back in my earlier days. And a Billiken, got my bachelor's at St. Louis University. Midwest kind of guy, grew up in Western Pennsylvania, lived in the Midwest almost all my life. From Pennsylvania out to Oklahoma, a few years in Texas. So I love to have these discussions around the focus in the heartland. And the fact that many of us, you don't realize that we are in flyover states. That's a real phenomenon. And especially when I'm working with USDA and we talk about the heartland and rural development activities, it's definitely a hot topic these days. And I'm glad to see the focus and the potential to make something bigger happen in this region wrapped around the GLBRC. So good morning, everyone. Thanks for having me. Thanks for being here. Hope to have a good discussion with you today, present some things that you haven't heard before, and be part of the dialogue. How many of you were at the session last evening? Quite a few. So you, unfortunately, are going to benefit from the old adage of the best way to learn is repetition, repetition, repetition. So several of these slides are in that vein. So bear with me. I will take a slightly different spin on some of this stuff, though, because I was asked to talk about a couple of specific aspects, the technology aspects, the policy and market overviews of SAF. So some of the things we dove into yesterday afternoon, we won't be able to do here, and my overall time is shorter. And I see that Deb was good up here with the hook of pulling people off the stage. Okay, so for the next 50 minutes, 45 minutes or so, these are the elements that I'm going to talk about. Jet fuel demand, our key driver. Jet fuel demand is expected to increase for the foreseeable future. Our industry is growing at about a 5% per annum rate, and it's not expected to abate from that rate because about half the world has never experienced aviation before. And these are people in countries that don't have the infrastructure for rail, even automobiles in many cases, and they're just coming to the level of economic development where travel starts to make sense for them. And I've experienced this firsthand working with partners in Brazil, where the only opportunity to go from two bases of interest was by bus for about a 27-hour travel trip, or by airplane for less than 2 hours, right? And so the value proposition for humanity in having high speed, safe, and efficient, don't fall into the trap that aviation is not efficient and growing more efficient, is a key enabler for societal development. So what does that mean at the end of the day? So we're growing at a 5% rate. That means our emissions, if technology is static, our emissions will continue to grow at a 5% rate. Well, for a lot of other industries, they don't have anywhere near that growth rate in mind. And in some cases, those industries actually likely shrink in their CO2 emissions over the coming years. So here we are growing while these other sectors are shrinking. So you find yourself in 2050 looking at the aviation enterprise as being maybe one of the top emitters of CO2 in the world. So that's problematic, and we're trying to react to that. We're able to introduce technology efficiencies at about a 2% rate. We've demonstrated that for several decades. So that means we've got a 3% problem, right? Growing at 5, reducing it to 3%. Forgive me on the hand-waving mathematics associated with that. We know that we can use sustainable aviation fuel, fuel made from hydrocarbon sources other than petroleum that deliver a net life cycle greenhouse gas reduction of actually any range. I've got 65 to 100% on here, but there's obviously solutions when they're delivered in small volumes are only going to deliver a couple percent. And we've got solutions that are actually well past 100% carbon negative fuels. The things that the industry is focused on are fuels that are in the 65 to 100% range, and there's a lot of examples of those. The aviation enterprise actually worldwide is aligned on these goals. We'll talk more about that in the policy section. In the US, that's about a 26 billion gallon market. In 2019, before COVID hit, that's the total level that we were at for all jet fuel used in the US. Commercial, domestic, business aviation, military, other airlines coming into the US and fueling up with fuel, 26 billion and about 100 billion worldwide. That makes us a gigaton emitter. That's really, it puts us in that class. All right, so based on the work that we've done for the last 16 years, what can I report today? We know how to make this stuff. We've got activities we actually have fuel being produced, so fuel readiness level of 9, to a sketch on the back of the envelope that Dave sends me every couple of weeks that says, hey, Steve, what about this idea? We're at very low technology readiness levels, and a full range of stuff in between. There's a lot of people working in the industry to foster, catalyze, enable, and facilitate continued development. We have more than 6 facilities online. We've only got a couple of dedicated facilities producing SAF worldwide, but many others producing them, like Tim showed with the refinery diagram, where they're producing SAF as part of their portfolio. A lot of commercial agreements being pursued, fostered by policy and other unique approaches. And I'm going to take a second just to do this because this is striking, especially for those of you who don't follow our industry closely. Can I do this quickly? Yes. So one of the struggles we're having today is keeping up with all of the activity that's going on and all the requests for assistance. But Jim Lane writes, puts out a daily missive called the Biofuels Digest, and this is today's. And this just goes to show the level of activity that's going on, some of it coming from people in the room. First, when Emirates operated its first milestone demonstration flight on a 777-300ER, powering one of its engines with 100% SAF, part of that SAF provided by Dave and his team. Asiana Airlines entered into an agreement with Shell Aviation for the supply of sustainable aviation fuel for 5 years from 2026. On the partnership side, ATR, working with the French government in Occitanie region, signed a declaration to advance the development of SAFI by Occitane. Travel Places is launching a new SAF fund, offering its business travel clients the opportunity to purchase SAF. And they're currently provided through a multi-year partnership with Phillips 66. On the capacity building side, an announcement Tuesday evening that made my day. Darling and Valero announced that they have made the financial investment decision on converting 50% of the Diamond Green diesel facility in Port Arthur to SAF production, bringing in 235 million gallons per year capacity by the end of 2024. ENG has received a $9 million award from Reconciliation Energy Transition for engineering and design on a 6,500 barrel per day SAF RD project in Calgary. And finally, market research firm Transparency Market Research reported that the global sustainable aviation fuel market size was 186 million in 2021 and is projected to reach 402 billion by 2050. So believe me, from when we started in 2006, there were a lot of days, weeks, and months that went past with no good news, right? Continuous struggle. But I think without jinxing anything, we're perhaps at the tipping point of seeing SAF go forward. That's driven by continued development of technology, the increase in policy mechanisms, both incentives and mandates, more aggressive posturing by people who buy fuel, et cetera. So I hope we're on our way, knock on wood. All right, so today, one of our potential impediments is that we have to blend fuels, and I'll talk more about that in a minute. And people recognize that that's a challenge for a producer here in the Midwest. How do I get Petrojet to blend with if I want to deliver my fuel to Madison? We can't, we're forbidden by regulations from actually blending that at the airport site. So we've got to come up with unique ways to do that blending. So the industry is off working on concepts around producing 100% SAF, fully formulated drop-in jet fuels. Additional work is needed on appropriate conversion processes for some targeted feedstocks. This goes right to the heart of Tim's work, right? Lignocellulose. We know we can hydrolyze the sugars. We've been doing that for years. And the big joke in the industry, at least from the one that I hear, right, is you can do anything with lignin except make money on it, right? And so figuring out how to get value out of that side of the stream and bring all that hydrocarbon to bear into those products is clearly the issue. And here's the number one takeaway. If you pulled me off of the stage or if I have a stroke in the next few seconds, our focus, CAFE's focus, CAFE working for the entire industry, our focus is on affordability. That's what's holding us up. And there's some real pragmatic issues there for folks like Dave to actually put together the business case to go out and build a 3, 4, how much, where do you want me to stop at? $600 million facility. Some of these facilities are in the $2.2 billion range now. And move forward. It's a tough proposition for somebody who's not operating off of a well-funded balance sheet. And my premise is that getting to that affordability enables acceleration. And the bottom line message to you as a team in this area is if you're focused on technology, business issues, et cetera, then enable that affordability through technology, through innovative partnerships with the state and regional governments, et cetera. It's going to help our industry take off. Okay? All the rest is filler. This is the current commitment that the aviation industry has made to achieve net zero CO2 emissions by 2050. So not physical CO2 reductions of carbon coming out of the tailpipe, but a reduction in the net life cycle of operating an airplane. I described the fact that we're basically a 1 gigaton industry sitting here in the 2019 timeframe. Got the decline from COVID. We're coming back nicely in some segments, but that growth rate that I talked about, that 3% average annual growth rate, is what gets you the 2x multiplier out to 2050. If we don't do anything, we'll be a 2 gigaton industry. So we have a complete portfolio of technology, operations, SAF, and market-based measures that are shown in that gray wedge, which are things that we're working on to go from that 2 gigaton industry to a net zero carbon industry. All right, just a few comments on the technology wedge, because people commonly ask at this point, was like, well, is SAF really the best option for you guys? Why can't you make a lot of improvement in technology and operations and rely more on market-based measures? And commonly the next question is, well, what about the announcements that have been made about hydrogen-powered aircraft? So I feel compelled in many forums like this to say hydrogen is a very viable fuel for some cases, or a feedstock in other cases. It's not necessarily viable as the energy carrier for use in aviation. The majority of our emissions, 95%, come from larger aircraft operating on longer duration missions. There's a lot of really cool work being done on very small airplanes up in this sector. So yeah, I'm not sure of the feedback. But the basic issue is that those technologies don't necessarily make their way onto a larger airplane platform. So you'll see stuff in the common press, you know, aviation is pushing forward on the use of hydrogen, fuel cells, battery power, full electrification, et cetera. But the trick there is aviation means everything that flies, right? Everything from a handheld UAV to the A380, a 2.3 million pound takeoff weight airplane, or sorry, 1.2 million pound takeoff airplane. But for where the majority of our emissions come from, these technologies don't work. They're off by an order of magnitude or more. And so this is the overall approach that we're taking is, yes, those other technologies might come into play over the next few years. We're not going to be on the bleeding edge of doing some of those things. We'll adopt them as we have with every other aspect of our industry. When a new material in the world is developed and is demonstrated in the marketplace, then aviation will often take that material and pull it into the airplane design or system design. So we're working a SAF and overall approach. We need it today. The emissions that we're producing today have an impact forever. So we need it today. We're going to be using it through the entire 2050 period. And I could be very wrong on when hydrogen fuel cell or hydrogen burning airplane might come into play. I'll be retired by then. So if anyone wants to make a lunch bet with me on when that'll happen, I'm happy to do that. So if I go back and look at that industry commitment, that long range forecast for how much we can achieve by when, and you look at different rates of technology incorporation, operations improvement, et cetera, those are the three blue lines at the top that says we need somewhere around 300 plus million tons of fuel. That equates to about 150 billion gallons or 9.7 million barrels per day. And our target in the US for that time frame is about 35 billion gallons. And here's a set of feedstocks that can comprise that level of fuel production. So at least today, we're clearly not feedstock short. Those are all waste streams. Those are not primary crops. And then you have the promise down here of power to liquid fuels. These are fuels that are using hydrogen and carbon monoxide. The carbon monoxide potentially coming from sequestered CO2, the hydrogen potentially coming from water electrolysis. And if we can bring the price of those technologies down, they might be able to compete with the technologies that we're working on today. But right now, the business proposition there doesn't look good. So we've done enough work in the US over the last several years that last year, actually, 2021, the White House announced the SAF Grand Challenge that aligns all the efforts of the individual agencies, the White House, and business on a goal to produce 3 billion gallons by 2030 and 35 billion gallons by 2050. So that's basically 10% by 2030 and replacing all of petroleum-based jet fuel by 2050. A lot of other people have made similar commitments. The other countries are doing the same thing. They're introducing policy, et cetera. We've got folks in the industry who are making the linkage between our need to generate credits at some point in the future to match our international commitments and how that marries up with SAF production through concepts like power to liquids fuels, through bioenergy carbon capture and sequestration, direct air capture carbon sequestration, et cetera. And we've got all of the OEMs, DOD and others working on R&D. So it's all coming together. All of that is the reason behind that, those headlines that I gave. So talked a lot about SAF. What is it? It's still an aviation fuel. So we're after a drop-in jet fuel that doesn't require us to bulldoze every airport in the world and build a new airport with a new fueling system. We're after a fuel that doesn't require us to park the entire trillion-dollar portfolio of airplanes in the world. All right, so we're going after a drop-in fuel. So it maintains the certification basis of today's airplanes. Secondly, we want to figure out how to do that sustainably, taking social, economic, and environmental progress into account with a clear focus on greenhouse gas reduction, but we're not losing sight of those other aspects too, right? So something that you might see if you're not necessarily a fan of it, the aviation enterprise, a common ad that's run these days is the best way to fry the planet is to continue to fly, right? And they have pictures of rainforests being bulldozed and polar bears falling out of the air and all manner of other crazy things. We're not blind to any of those issues. We're trying to do this in a sustainable fashion, hold our feet to the fire. But everything that we're doing so far is looking great. So how do we do those first two things? Well, it's simply by creating a synthetic jet fuel. So instead of reaching into the ground and pulling out petroleum for our next flight, we are reaching into our biosphere and pulling out hydrogen and carbon molecules and converting those into jet fuel for our next flight. So basically doing a mega recycling of hydrogen and carbon in our biosphere. And if we get to negative use fuels, we'll actually start to reduce carbon in our biosphere. We're a ways from that, but we're working in that direction. Unabashedly, this strategy that we laid out in 2005 through 2007 has withstood every test so far. There was a tremendous amount of thought process that went into this strategy before we rolled it out. And unabashedly, we believe it's the lowest societal impact way to decarbonize civil aviation and continue to provide this means of safe, high-speed transport that people need, that the world needs. So the specific things I was asked about: technology, policy, market. On the technical side, they're increasingly technically viable, still struggle with economics. But we know we can produce those using numerous pathways. The aviation industry has approved 7 ways so far to do that. I'll talk about those. There's another 6 in process. Someone in the room might be adding another one to that list later this year. There's at least another 15 that are further up the pipeline. 4 pathways are expected to go to ballot in 2023. So we might wind up with 10 or 11 pathways by the end of the year. Some of those actually might be derivatives of existing pathways, but nonetheless, there'll be new ways to produce these fuels. These pathways enable the use of all the major sustainable feedstocks, things that nature is handing us: lipids, sugars, lignocellulose, hydrogen and carbon sources, circular economy byproduct streams from our own manipulation of our biosphere. We do this by using thermochemical and biochemical conversion processes to produce the pure hydrocarbon molecules that we need for jet fuel from these very, I was going to say unusual, but it's nature, so I shouldn't say unusual, but from hydrocarbon forms that aren't so conducive to being jet fuel in their natural form. We do have some blending restrictions I mentioned before. After that initial blending is done, whatever remains, the blended component is jet fuel at that point. Fully miscible with the existing jet fuel, can go anywhere in the system that jet fuel does. So just that first blending that does need to occur, after that, it's good to go. And we're doing some work with co-processing at refineries. All right, so this is what jet fuel looks like. It's a mix. People use different numbers. Some will say C8 to C16, like you see on the left-hand side of this chart. If you look in more detail, you actually get some tails in there of C7 to C17. You can even occasionally get some stuff that's C6 to C18. It just really depends. This is an aggregate view. The fuel coming out of every refinery in the world looks different. Those fractions will be different. They'll be skewed in different directions. This is what we're trying to replicate. If we get a fuel that looks more or less like this, it will meet the certification basis for our airplanes. It will be truly a drop-in fuel. The challenge that we have in working with these 7 different pathways that we have, depending on the feedstock and conversion process that you use, I don't get something that looks like my pie chart. Those variations will change significantly, or in some cases, I get no aromatic content at all and very, very little cycloalkanes, and so very much a paraffinic fuel. And paraffinic fuel will burn fine in an engine, in an airplane, but it doesn't deliver all the characteristics that we need for full interoperability. So we're working on ways to address that. That's why we have the blending requirements. Talked about this yesterday a little bit more. This goes hand in hand with this concept of us needing all of those molecules that are shown there for use inside the airplane engine, because the fuel doesn't just get used to burn, to convert the chemical energy into thermal energy. It's used as a coolant, as a lubricant, as a hydraulic fluid, a ballast fluid, a swelling agent, a capacitance agent on board the airplane before it finally makes its way into that combustor. That's what the inside of a modern combustor looks like, and burned. And along the way, it has to do a lot of stuff. And so those characteristics of having C7 to C17, iso, normal, cyclo, paraffins, and aromatic content are important to us. We've got to have high energy content, both volumetric and on a mass basis. If I do shifts of that pie diagram, I get changes in volumetric and energy per unit mass. Sorry, energy density per volume and mass, both. And one might be good for a commercial customer and bad for a military customer, and vice versa. So we're sort of threading the needle with putting requirements on what these ASTM fuels need to look like. Those are specs. If you want to dig into actually what we're doing, you can take a look at those specs. If you want to get more involved with that, you're welcome to join ASTM. Join this community that's evaluating the development of new synthetic fuels. This is the process. It's convoluted, but the reason that it's convoluted is because every piece of equipment manufacturer who touches the fuel wants to make sure that these fuels are not causing deleterious effects. So we've got this rather sophisticated tier 1, tier 2, tier 3, tier 4 process that someone walks through to get approval from the major OEMs that yes, this fuel will meet their requirements, or if it doesn't fully meet their requirements, will there be blending restrictions on those, et cetera. And what you wind up with at the end of the day, after going through that process, is the aviation industry itself votes on the approval of these fuels. And if they're approved, they're added to annexes at the back of D7566. And so those are the existing 7 annexes that we have. We also have approved the addition of co-processing in existing refineries. Those don't fall in the 7566 spec. They fall into the 1655 spec. It's just our way of handling some key differences. And in the gray box at the bottom right, you can see that we're working on an additional 3 co-processing expansions. The good news in all of this is, well, it depends on your perspective. A twist on this perspective that's really come around in the last couple of years is that the existing producers of petroleum jet fuel are now fully engaged in the process. And so those 2 of those 3 expansions shown over in that gray block are actually being driven by large petroleum companies. And just recently, yeah, I added it there. Top green block here in testing initiated, 7 companies in December came forward and said, we would like to add methanol to jet to the alcohol to jet pathway. And most of those are very big players in the petroleum space. And they're looking at being able to take advantage of the methanol production that already exists in the world and the direction that we're going with respect to the use of renewable gas to produce renewable methanol that could perhaps mean big things for our industry. So we'll see how that goes. All right, talked about this. This is sort of a summary. I take hydrogen and carbon feedstocks. I do some conversion of them using biochemical and thermochemical processes, and I produce something that looks like a bio crude. In some cases, I can take that straight to a refinery and have it co-processed at that refinery, or I can have standalone refinery processes like hydrotreatment, hydrocracking, isomerization, and distillation to pull out that jet cut from that bio crude. And then I have this SAF blending agents, and those are the things that are described in those annexes. Those are pure C7 to C17 hydrocarbons that are suitable for jet fuel, but perhaps not fully enabling of being able to use them as jet fuel. Then the important issue, we've got to blend those. And when we blend them, we get rid of those final nagging issues about whether it's fully formulated or not. And then after that, it's fully fungible jet fuel. All right, there's some detail on the 7 pathways. So you can reference that chart instead of going out and paying a couple $100 for the spec on your own. You can see in the last 2 columns on the right, the technology licensors for some of those technologies, as well as some of the entities that are out there commercializing, actually physically building plants for the use of those processes. I talked about that. I'm going to skip over that. Here's an example of what's happened in the last couple of years with respect to co-processing at existing refineries. And here's the driver. The EU, 3 countries in the EU already have blending mandates that apply to jet fuel producers. If you want to supply jet fuel in the EU to an airline or other user, you are mandated to have, in Sweden and Norway, I think it's 1% today. In France, I believe that it's ratcheted up to 2%. So in the last couple of years, what you've had is these refiners have gone off and demonstrated their ability to co-process and deliver those levels of renewable content in their jet fuel. But what they're really looking at is what's about to happen in Europe, which is a blending mandate that starts in 2025 and ratchets up significantly to achieving a 63% level in 2050, and a sub-mandate that says, okay, we'll give you need renewable molecules in your jet fuel, but a sub-mandate has to be, some of those molecules have to come from PTL processes. So utilizing CO2 and hydrogen. So the Europeans are getting ready for this. This will We expected this to be finalized last year. It's still in a lot of negotiation about how stringent that should be and some other aspects that are going on, but this is going to come out imminently. All right. So I said on page 1, the challenge is affordability, right? So, and you think, why can't the airlines raise their price and cover the cost, right? And you got to look at that pragmatically. It's like someone coming to you and saying, okay, in your own personal case, I need you tomorrow to start buying renewable electricity for your home and renewable fuel for your car and several other renewable aspects that could immediately impact your budget. And you don't necessarily have the flexibility to do that. And we don't necessarily on the aviation side either, because we've got some very poor behavior on the part of users of the aviation enterprise who do stupid things to save $10 on their airline ticket, like taking an extra stop or stopping for 4 hours at a hub instead of 3 hours. Just some non-sane behavior on the part of buying airline tickets. Several airlines have experimented with the ability to pass this cost along to their customers, and it's starting to take hold. We'll see. Just this past week, Air France announced that they very publicly came out and said, okay, because the French government is going to force us to blend 2% of this renewable fuel into our overall fuel pool, our cost is going to go up, and we're passing that on to the customer. So there are some examples where it's starting to take, it just is going to take the industry a while to get their heads wrapped around exactly how to do that. So the other side of the coin, which you guys have some control over, if you're not working for an airline, is how can your work help to reduce the production cost of the fuel, right? So a lot of things on the technical side, like catalytic processes that continue to come up. Can we use catalysis in the conversion process more effectively or in different ways than we hadn't thought of before? Can we get higher carbon utilization rate out of the feedstocks that we drag into our refinery, right? It's a fixed cost. I got to pay X dollars per ton to have the stuff delivered to the refinery. And if I'm only able to capture 48% of the carbon and the rest of it goes out as a waste stream, it's painful, right? So if I can get that from 48% up to 70%, 90% carbon utilization, let's go after that. Systems that obviously offer lower CapEx, lower OpEx, figuring out how to integrate systems at the refinery, finding higher value for production slipstreams and byproducts, which fits right in with the comments that Tim made about looking at the full barrel kind of approach, capturing value from other environmental services. Can we make agriculture or our land use much more sustainable going forward? And are there ways for that segment of the value chain to capture some of that value? So there's a steady stream of those kinds of examples. I'm just encouraging you that if you're interested in seeing aviation be successful going into, and you want to control, so that you can think about the processes that are being used to produce these fuels. Okay, so that's it for technology. And how am I doing on time? All right, policy. This can be an hours and hours kind of discussion because it's and a lot of moving parts. But let me try to bite it off this way. Good, bad, or otherwise, aviation is bifurcated. International aviation, all of the fuel burned on an international flight, all the emissions under one overseer. It's a UN body called the International Civil Aviation Organization, ICAO. All domestic emissions are expected to fall under the states in which those flights originate, under the purview of state governments. And the expectation at the UN level is that those state governments have their own compliance plans to meet their Paris commitments. All right, so that's how aviation is governed. On the international front, we have an international mechanism in place. It's called CORSIA, the Carbon Offsetting and Reduction Scheme for International Aviation. And it basically caps emissions at our 2019 levels forever going forward. and it shoots for that aspirational goal of net zero in 2050. Carbon mechanism that allows us to make up for the fact that we're not making enough progress technically. So an airline, if they exceed their emissions from 2019, can purchase offsets in the marketplace, or they can use lower carbon fuels to reduce their obligation under that scenario. It's a rather modest proposal today, and in that they will accept the use of SAF that only delivers a 10% benefit. They will actually accept the use of carbon fuel that only achieves a 10% benefit. So it was an international consensus body, and you can see that consensus in every ruling that they make. And that 10% LCAF fuel, low carbon aviation fuel, came from the folks in the Mideast, as you might imagine, who said, you can't kill us with this thing. Let's figure out a way that we can work together on this. So a 10% carbon reduction on petroleum-based fuel is nice, but it is not trivial, because so much of the carbon is baked into the fact that I'm pulling hydrocarbons out of the ground. So if I want to make an overall 10% reduction, I basically have to completely retrofit my refinery and convert it to renewable power, et cetera. So it's a tall task, even with that that agreement to use 10% lower carbon LCAF fuels. The U.S., as part of what I described as meeting their Paris commitments, the U.S. has a strategy on reducing the carbon associated with aviation. And that shows up in the SAF Grand Challenge and the policy things that are going on. So in the US, we have an RFS, renewable fuel standard at the federal level. We have federal tax policies, incentives at the federal level, and then at the state level, and those are growing. Right now, we have low carbon fuel standards in California and Oregon, and one is being promulgated in Washington. Maybe shouldn't have put this on the slide. There's a tax abatement bill that has made it through the legislature in Illinois. As I checked last, it hadn't been signed by the governor yet, but it's a very unique incentive that basically allows an airline to abate the taxes that they pay on fuel, the state taxes, and get credit. So it's a way to credit the use of SAF through an existing tax mechanism. And then there's a bunch of other states doing similar things. And I already mentioned on the national framework, the EU blending mandates that are on the way. The big issue in all of those metrics is that they typically are counting on the delivery of a life cycle assessed level of carbon lower than the baseline. And so you can go out and look at this document for free. It's the Core CF framework that describes baseline levels of carbon reduction associated with a whole bunch of different conversion methodologies and feedstocks. So this is the one on just hydroprocessed esters and fatty acids, Annex 2, basically fuels made out of fats, oils, and greases, and in different countries, because they're assuming things like, what's the baseline carbon load associated with the electricity that you're using in country, et cetera. But you can see the reductions there. You can also see that, for instance, palm oil from Malaysia and Indonesia comes out with a final score of 99.1, which happens to be baseline of petroleum-based jet fuel of 89.1. So no palm oil from Malaysia and Indonesia will be used to meet. So this is one of those areas where our industry is saying, on a overall sustainability basis, when you look in detail at life cycle assessments, some feedstocks are not going to pan out, right? So there's a large body of work going on behind that. Challenge. The latest thing that has happened is the execution roadmap for that overall agreement was released a couple of months ago. It has 6 primary work streams in it that are highlighted in those sub-bullets. There's a lot of work going on. There's already money coming from federal agencies that go to execute some of these projects. And there's a list of examples. And so you can see in some of these cases, it's real money. To some of you, it might be real money, right? 65 million over 22 projects. But look at line 3, 2.8 billion came from USDA awarding the Climate Smart Commodities Program. And I don't know if you guys touched that directly or not. There's a lot of really interesting projects in there. Not all of those will translate to SAF production. There's a really wide range of projects, but 70 projects pulled in 2.8 billion. And then a couple months later, they announced an additional $500 million for smaller projects. So $3+ billion spent on feedstock development. Quite a few other activities. The most recent one that was just last week was Beto announced their latest accelerating biofuels development for 118 million over 17 projects. One of those getting the lion's share of 80 million to stand up a demo biorefinery with a new production process. So this goes back to the statements that I made originally. How are we doing from a market perspective? Things are going nicely now because we have all of these buyers coming to the table. Airlines, business aviation, scope 3 users, right? These are corporations who part of their total carbon portfolio is comprised of their people flying on airplanes. Those are scope 3 emissions for that company. And that company wants to abate those emissions. And they have shown fairly aggressive tendencies towards how much they're willing to pay to abate that carbon. Really good news. It's something that really wasn't expected 15 years ago, but some of these companies are rather aggressive. Suppliers, freight handlers. The freight handlers lately have made some additionally aggressive approaches. So UPS, FedEx, Polar, Airborne, DHL, et cetera. They're active in projects, they're buying fuel, they're involved in research and development activities, et cetera. Regulators and policymakers are helping us out. There's 5 examples of things that have happened in the Biden administration: ARP, the IIJA, SAF Grand Challenge, the IRA bill, which was huge for our industry if you haven't looked at the details of that. So that's all moving in the right direction. Third parties now are starting to also come to the table and say, what we're really interested in is carbon removals at the end of the day. We applaud your efforts. How can we help? So Breakthrough Energy Collaborative came through with a pretty significant loan to get the LanzaJet facility, help assist the LanzaJet facility building their facility, which will come online this year, right? And then technology developers are getting more involved. We got international collaboration going on, et cetera, et cetera. And you say, okay, Steve, that sounds nice, but where are we really at? And this is where we're really at. Last year, we used in the US just short of 16 million gallons of jet fuel. Okay, so recall what I was talking about before. 16 million out of 26 billion. We got a ways to go, right? Our near-term goal is to get that number up to the 3 billion gallons that was committed to in the SAF Grand Challenge, and it's like all hands on deck right now trying to make that happen. Worldwide last year, across the world, in multiple countries, almost every sector of the world, nothing in Africa, nothing in Antarctica, 80 million gallons of SAF production. So 80 million out of 100 billion, basically. All right, even digging more into the weeds with Steve. All right, Steve, well, how are you looking with respect to the 3 billion gallon goal? So sitting at 15 million in 2022, we expect a couple of facilities to come online this year, and that projected level of increase through 2028. You say, it still looks a little bit short of 3 billion over the next 2 years after that. And the good news is that people continue to get added to this chart on a continuous basis. In fact, I put the latest 2 announcements on there, the Port Arthur facility at the top of 2025. That's this week's announcement. I threw tall grass on here. I usually don't do this, but I put it on here just for the purposes of discussion in this session, that an announcement was made that United Ventures invested in this company this week, and they have the potential, or they have the appetite to produce 135 million gallons by 2028, a new process. Whether they can achieve that in that 5-year period remains to be seen, but it's nice to get that level of investment. But here's the important thing from my perspective, the reason I'm not panicked or can't sleep at night, that I'm not sleeping at night, I should say, is that there are 160 additional new entrants that are not reflected on this page. Perhaps 50 of them are charlatans, right? They come and go. I try carefully not to avoid anyone coming into this sector and exploring it. I may choose not to spend much time working with them as opposed to other entities who have a great level of interest in. But we know, these guys will come and go. And I made the comment before about that Port Arthur announcement this week that was a good thing, because I've also been on a bit of a downer the last few weeks with respect to Red Rock, which was previously in that blank slot at the top of year 23. And it looks like they are not going to make it, and that they are going to be auctioned next week. Facility that was more than 50% complete couldn't make it to the finish line. So very unfortunate. These things will come and go. All the things I talked about on the fuel qualification page will come and go. The advent of fuel production from methanol can make a huge difference in this time frame. And then it's also important to point out that second line in the blue oval, LanzaJet, Gevo, Alder, and Fulcrum themselves have suggested that under the right conditions, they each would like to be able to produce 1 billion gallons themselves in this time frame. So we'll see how that goes. You have some of those folks in the audience, and you can ask them about that. And then another recent twist that perhaps shows why the Port Arthur facility made it onto this list is that the IRA created a completely different paradigm on the policy side by rewarding SAF production more than renewable diesel production. So the 6 billion gallons of renewable diesel capacity that was planned for this time frame, all of those folks are taking a look at policy and saying, should I think about the SAF space instead? All right, I can't take one question without impeding myself too much. Yes, sir.
Quick question. Are the commercial airlines investing in any of these facilities for B? Are they signing off-take agreements with them? How does that work?
Yes, both. Not much investment, but some. I talked about one case already. But yes, off-take for sure. And this is the airlines have said to themselves, hey, I never worked upstream of my fuel farm in the past. Does it make sense to do that now, to venture out into upstream investment to bring this off? And in general, they've all said, no, this is not a space that we want to go in. But the incentive that they've been offering to these producers is we are willing to give you 5, 10, and up to 15-year offtake agreements for the production of your fuel, which petroleum producers can't get in any other sense. So it's a very big incentive. But there's still some natural market tension there, right? Between what they want to pay for it and what these companies want to contract it for. But nonetheless, it's happening. And so this is my next to last slide. It's not all rosy. I think you got the half glass full message from me today, but these are real things that are happening out there. We've got some groups in Europe who are basically working actively against the aviation enterprise. And they're starting off in the business aviation sector. And so a person in the Green Party government actually called for a complete ban on the use of business jets in the EU. That got overruled, thankfully, but there's still that sentiment that's out there. France, you probably don't, this is not highly discussed. France actually eliminated domestic flights in France that could be completed in less than 2.5 hours by train. They did. They eliminated them. You can't fly that route anymore. Luckily, that's only 3 routes so far in France, but it's on the way. And then we got friends like our folks in ICCT who are out there constantly goading and pricking us to say, hey, you know, figure out different ways to do this. You got to pass this cost on. You really need to abate the amount of travel that's going forward. You don't need to be growing at a 5% rate, blah, 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 frequent flyer taxes, et cetera. So there's that negative side of things going on out there. Back to where I started, pathways are identified for fully synthetic fuels. We're working on that. That'll happen within the next 18 months. That could really change the game in some fashion, not for everybody, but in certain cases. It could allow exactly what Dave has been executing lately. He is partnering with a producer of SPKs, blending those 2 components together and producing a fully synthetic jet fuel that's being used in a lot of examples right now. So we might see more of that. So these local solutions of taking Virent fuel, blending it with somebody else's fuel and delivering it to Madison is a viable scenario going forward. And then finally, the important thing is we're doing all this other stuff on the policy technology side, but from your own perspectives, are there things that you can do to continue to enable affordability, because that affordability will accelerate commercialization, and we can use all the help we can get on that front. And with that, I'll stop. And am I completely exhausted on time? 42? Yeah. Okay. Got any questions? Feel free to pull me off on the side. Thanks. Yep. All right.
All right, so now we're going to switch and look at the overview on the bio-based chemicals side of things. And we have Brent Shanks. He's an Anson Marston Distinguished Professor of Engineering and the Mike Jean Stephenson Faculty Chair in Chemical and Biological Engineering at Iowa State University. He established and served as Director of the Center for Biorenewable Chemicals, formerly a National Science Foundation Engineering Research Center. Brent is the co-founder of Pyron Systems, Inc., which is commercializing Pyron technology developed in Seaburg. He is on the advisory boards for the Plant-Based Products Council and the DOE Bottle Consortium. After receiving his BS degree from Iowa State University in 1983, he completed his PhD degree at the California Institute of Technology in 1988. And from 1988 to 1999, he worked as a research engineer and department manager in the Catalyst Department at the Shell Chemical Company Technology Center in Houston, Texas. He joined the faculty at Iowa State University in 1999, where his group's research has primarily involved reaction systems for efficiently converting plant-based feedstocks to chemicals. So with that, I'll turn it over to you.
Thank you.
Thank you.
So I think it's really important the transition from Steve over to this space is I want to emphasize that there's, I think, a lot of misconceptions about bio-based chemicals and bioproducts. And I'm going to mention some of those that come through, and some of the folks in the room may not like the take I have on it, I'll admit right from the start. But I would like to walk you through. I was asked to talk about market, technical, and policy. That's not a, well, you may find some typos in these slides. That is not a misperception where policy is listed there. It's lowercase, smaller on purpose, because as complicated as policy is in SAF, it's way more complicated, way more nascent, way more fractured in the bio-based chemical area. So it's really difficult. There is no governing body equivalent to, or even multiple governing bodies to address it. So there isn't a really cogent policy statement to make, but we'll talk a little bit about some things that are kind of creeping around the edges on that. The first thing, and I'm going to spend actually some real time on this slide because there's really a tremendous amount of important information. And I think, again, maybe bursting some bubbles of some thoughts that misconceptions of what bio-based chemicals look like. So let's start on the left. So this is from 2019, the production numbers for really the largest petrochemicals that are produced. And this is the US production, which is about 12% of the global production of bio-based chemicals. And I've and ethanol is only on there because it's not produced petrochemical, but I wanted to just contextualize the size of these markets relative to ethanol. So as you can see, already, even with ethanol, which from a fuel perspective is still not enormous, it's still larger than any single bio-based or any single chemical product that we would be talking about. So actually the ethanol industry is quite large relative to the chemical industry. The second biggest, and so then the next thing to look at is the yellow molecules. Those yellow molecules are essentially the primary molecules that the petrochemical industry makes. So why did the petrochemical industry come into being? It wasn't to subsidize fuels, by the way, and we'll talk about that at the end. What it was we had a light gas stream that was being flared. And in fact, if you took a picture of the world at night, even in up to 2000, you would see this bright light over Saudi Arabia because they still flared their light gases because they didn't have chemical technology that they could purchase to use for that feedstock. And in fact, unfortunately, we still have this going on in North Dakota where the oil shale is going on. If they have too much little gas coming out, they're still flaring gas. It's a horrible thing, but that's the reality. And so you have this light gas stream that are alkanes largely, and those alkanes are then sent through a cracker, and out of that cracker comes these alkenes that we can now do chemistry on. And so those are ethylene, propylene, not methanol, we'll come back to methanol in a second, toluene, benzene, paraxylene, butadiene. Now, in Europe, they use naphtha for theirs as opposed, so they use heavier, so they have more aromatics than in the US. And in the US, we subsidize or we augment this benzene, toluene also comes off the refinery. So there's these light molecules that have to be removed from gasoline that get dumped into the chemical pool, essentially. So they're not all out of the cracker. The other major one up there is methanol. We've heard methanol, people are looking at oligomerizing that to fuels, but that one's actually comes from methane. But those 7 molecules are really the basis of the chemical industry, of the petrochemical industry. Okay, I've thrown ammonia up there as well, again, somewhat for reference, just so that we know what its size looks like. Ammonia, again, largely comes from methane, again, is its source. So you can just give you some idea of size. You can tell by far ethylene is the largest produced. The biggest use of ethylene by far is polyethylene, a plastic from it. But I think what you can see in this chart is how rapidly the volumes of these things go down after ethylene and propylene, and they get much smaller. I put acrylic acid and adipic acid on there because those are ones commonly mentioned for bio-based, which makes sense because they have pretty high oxygen content. So you can imagine those would be ones to target from bio-based. But it gives you some idea of scale of those. If you go all the way down to number 50 on the chemical list of petrochemicals, and to Steve's point, there's thousands of chemicals. But if you get down to number 50, you're down to only about 1% of the amount of ethylene that's produced. So already pretty rapidly, the volume of these things gets down. So one thing to know for sure in this, there's hundreds of chemicals, very large changes in the amount of volume associated with it. And getting small, relatively small quite rapidly is the problem. Okay, so that's the petrochemical industry. What does it look like if we look at the volume that's in place for bio-based chemicals worldwide? And this is from a IEA Bioenergy report. So that's the global production. I apologize, the units have changed somewhat, but at least, so this is 1,000 metric ton, but versus million metric ton, just so you'll know. You can see where ethanol sits globally. And so actually you can see quite a large percentage of that is actually in the United States. But then the next 3 or next 5 I show in green would also be on this left chart because they're primarily produced by petrochemicals. This is the amount of those that are produced by bio-based. Okay, so we are making bio-based ethylene, ethylene glycol, methanol, ethylene oxide, and acetic acid. A lot of those are coming from ethylene. And that just simply comes from dehydration of ethanol is the main source of where that's coming from. The next ones down are, you can see larger volume ones. And those are largely molecules that we do not make from petrochemicals. So we can already see the bio-based products, bio-based chemicals that we largely have globally are those that we can't really make from petrochemical sources. The one exception is glycerol. There used to be a pretty significant glycerol production process, but that is now shut down. Biodiesel has completely killed off the petrochemical route to glycerol. So all glycerol is now produced from biological sources. These are really important charts. And to realize then the complexity associated with bio-based products, because while jet is actually the most dramatic in terms of the fuels, in terms of specs and the range of molecules you can have, it is still a mixture of molecules, as is gasoline, as in diesel. Diesel, it's a mismatch of a lot of crap. Gasoline, a fair amount. Jet is actually the most stringent of all of those, right? But this is even more stringent. This is a specific molecule that we are making. And we have to remember that. These are 99% plus purity that we make these in. And we don't get to bleed in 2% of some other molecule. So all of a sudden now, separation costs, which is very rarely spoken about, becomes tremendously important. And lots of times is more than 50% of the cost of production is the separation, not the conversion to the molecule. Okay, so the other thing I should forewarn is I did spend 11 years at Shell in the petrochemical industry. So my view on bio-based chemicals is highly skewed through the lens of what I experienced in the petrochemical industry. So please take that for what it's worth, because that will certainly come through in terms of how I look at this problem and how I will present the problem. This is a really dated chart. A number of these companies are now bankrupt, but it was a beautiful chart that ICIS made that showed the sheer complexity of the bio-based chemical market. So in 2013, there was all this hype about bio-based chemicals. This is when crude oil was about $120 per barrel. So all of a sudden, economics of a number of things were looking more promising. You can see the dark gray were ones that were, they called it commercial stage. You'll notice that some of these haven't really, like PHA didn't make it, for example. So even though it was commercial stage, it didn't happen, and metabolics doesn't exist anymore. And then the ones that were in the pipeline, and some of those now have come to fruition, a limited number. Farnesene has from Amyris. What else has come? Epichlorohydrin certainly is happening. 1,4-butanediol, there's a plant being built in Iowa with Genomatica technology to do that. But look, this is an incredibly complicated, incredibly number of players. But if you count this, this is still only 30 products, right? Out of literally hundreds of products. And so this was the landscape in 2013 that ICIS could largely talk about in terms of what is being made. So this is only a drop in the bucket of chemicals that we could make. And it shows the complexity associated with going after this, because look at all the different companies involved with this just for this 30. Okay. Well, then along came synthetic biology. And I love this. This used to be Amyris's front page. And it is a beautiful picture, you know, remaking the world one molecule at a time. And it sounds so wonderful, except for the fact, if you think we have literally hundreds and thousands of chemicals, how many different organisms would we need to have to make hundreds and thousands of chemicals? Well, hundreds and thousands of organisms. Call me skeptical. As beautiful as synthetic biology is, are we really going to make 1,000 different organisms to make 1,000 different chemicals? Is that a practical solution? I just throw it out there to think about. There's still a belief around this that if we just get better at the design, build, test, learn cycle and do it faster and faster and faster, that we can do that. Maybe. Again, I come from a petrochemical background. Call me a little skeptical on this one, and I'll show you why I have that skepticism coming up. But there's been large investments. The Agile Biofoundry by the Department of Energy, the idea of tell me what molecule you're going to make, and I'm just going to make an organism to make it. DARPA has also invested significantly in living foundries to do the same thing. Okay. Even if you're going to realize that situation, the biggest problem is going to be what is the right target molecule to make, right? I mean, if I'm going to do synthetic biology, design, build, test, learn cycles, what is it that I'm going to make? In fact, I get this all the time. Admittedly, I was 6 years ago, JBay brought me in to be part of their bioenergy center. And the first question, I think the only reason they brought me in was because they said, tell us what we should make. And my answer was, and what I'll try to talk about today, the question you should be asking is not tell us what you should make. It should be, how do we decide what to make? And that's what I'm going to try to talk about today, is how we make that decision process of what to make. Okay, we have, in the meta sense, we have a couple of buckets that we can talk about. We can talk about direct, or what we would call functional replacement. And functional replacement would be a slightly different molecule, but they gave the same functionality as the direct petrochemical molecule. Obviously, what you would want would be expensive to produce from hydrocarbons, high oxygen content, so you can retain as much mass as possible from the feedstock. You worry about market size, greenhouse gas emissions, and consumer opportunities. There's certainly some consumer products where you can get a premium for bio-based chemicals, but it tends to be like products you use in your home, things like that. So there are specific niches where you can get some value add for bio-based. The other area, and this is where, again, maybe I'm overly pragmatic, but I think this is where there's the greatest opportunity for profitability, is performance advantage. Because now you can't, we saw in the original tables, a lot of those bio-based chemicals that were produced were unique to bio-based. They weren't competing against petrochemicals. So I think there's that opportunity. The challenge with that is, how do you demonstrate that performance advantage in a compelling way? And inevitably, it's going to be a small initial market size. So one of the themes I would like to also carry through this, there's some question of what do we do today versus what is our dream state in 2050? And I would suggest we sometimes live our life in the dream state and don't think through the practicalities of how do we get from where we're at to that dream state. And so I want to talk a little bit about that as we go through. There was a nice study done here at Wisconsin a number of years ago. I think this was funded by the GLBRC, I think, where they were looking at really trying to establish targets. And this, in case, was really looking at direct replacement. So what they looked at was the high production volume chemicals there in the left, off of the US EPA chart. They looked at the biochemical databases, KEGG and Metapsych, and said, where was there overlap between those? And they found 691 molecules that there was overlap between those. They then put those into metabolic models, looked at economic models, and then came up with some promising products. I would encourage you to go out to, I think the slides are going to be distributed. This was a nice effort to try to constrain what target we should look at. So I give a lot of credit for that. However, again, this is with the strategy of one product, one organism, right, was the strategy. So I want to back up again and say, is that the way the current chemical industry works? Well, absolutely not. As to the previous point I made at the start, these are the 7 building blocks. This is the petrochemical industry. I always feel silly and a little ironic using a tree as the exemplar, but I have put dark stuff down here at the bottom. So that's the crude oil. And you get these 7 products, and from these 7 products, we make all those hundreds of products, and those are like the leaves on the tree. So really, if we're talking a biofoundry, if we're going to do one product at a time, we're going to say we're going to recreate this tree by making one leaf at a time. Strikes me as an impractical proposition. So, is there some other way we can look at bio-based products? Well, one of the first things we looked at CBRC was, are there certain metabolic pathways that can be generalized so that we can, with slight modifications, move to more different products? That seems like a kind of an equivalent to a tree, right? Where now it's a metabolic pathway is a limb. Okay, so our metabolic limb in this case was fatty acid biosynthesis. Okay, and fatty acid biosynthesis is beauty. It starts with acetyl-CoA and malonyl ACP. They condense, they form the C4. And the way we make longer chain fatty acids is they just go around the cycle. So they start with a C4, C6, C8, C10, C12, et cetera, goes around the cycle. And what the organism does is terminate at different chain lengths. And that's how you get our different fatty acids. Beautiful biology, actually. I mean, it's way the heck down there. It's hard to get carbon flux through there. And the other problem, of course, is fatty acids are required for organisms. They put them in their cell membranes. So it's an important part of their existence. So because of that, it's highly regulated by an organism. And so we did a simple metabolic modeling and some flux analysis data for different chain length fatty acids. And we looked at what genes needed to be upregulated, downregulated to get to these different chain lengths. And our hope was that we might have 8 or 9 interventions that in this Venn diagram would get us through the fatty acids pathway, and maybe 1 or 2 unique interventions for each chain length. Doesn't look like that. So we had to get very different interventions for different chain lengths. Why is that? Because this pathway is amazingly regulated in living organisms. Okay, so we got a little frustrated and said, okay, we can't make metabolism diversification a limb on a tree. Some may disagree with me, but that's where we ended up with as a center. So we took the next step and said, well, maybe what we ought to look at is use metabolism to do what it does well, and then diversify with chemistry to a range of different products. And so this is where our center started to go with Seberg, was this sort of, let's make a molecule biologically and then diversify that to a range of other products. So, in fact, we're not unique. Other people thought about this. One of the ones I mentioned, acrylic acid, is one of those that is highly desirable from a consumer perspective. Most of acrylic acid goes into polyacrylic acid, which largely goes into baby diapers. And people are willing to pay for green baby diapers. So this has always been a glimmer in the eye of Cargill to go to acrylic acid. And it turns out, if you look, biologically, a great way to get there is if you can make 3-hydroxypropionic acid, then the dehydration step from that terminal carbon is trivial to go to acrylic acid. And then not only that, but 3-hydroxypropionic acid has a number of other products that can go out to. And I give a huge amount of credit for Cargill. They were dogged about this molecule, dogged about it, and did great stuff with it. Well, what happened, though? Well, what happened was it's been a long-term target for them, clear market demand, attractive attributes, all those things that you could want for a target molecule. Very rational decision by Cargill. And unfortunately, they cycled through many partners because it was taking a long time to do this. And in fact, what's happened now, though, is in the meantime, Procter & Gamble had been working on this problem because they want bioacrylic acid. And they came up with a catalyst that could actually dehydrate lactic acid, which is not as trivial to do as the terminal. The secondary carbon to get high selectivity to acrylic acid is a very non-trivial thing. And they came up with a catalyst that could do it. So in fact, this is now, to my knowledge at least, the preferred route that Cargill's looking at. And why would you go to lactic acid? Because they already make lactic acid, right? So it's leveraging existing infrastructure in doing this. So it's a very rational, good strategy. They are not the only ones doing it. Of course, ADM has now partnered with LG Chem to do the same thing. And 3-hydroxypropionic acid's kind of gone on the back shelf for this application. Okay, let's give another example of where thinking of biology and chemistry together is important. One of the things that JBay had been working on when I joined 6 years ago was they loved paraxymene. Paraxymene was this nice molecule that could be converted into a number of different things, not the least of which was a nice gasoline fuel. And so they had been working on engineering an organism to make limonene. The last step from limonene to paraxymene is hard to do biologically, so they were already doing a chemical catalyst step in that. Oops. So we went back and looked at it and said, well, if we look at the metabolic pathway, there's this intermediate metabolite, the GPP, that's produced that in fact, you can go to limonene or you can go to 1,8-cineol. And 1,8-cineol is just a hydrated form of limonene oxide, it turns out. It doesn't turn out to be the metabolite right before limonene, but that's all it is. It's just limonene with a water molecule in it. And when you look at that from a chemistry perspective, you see a ring, an oxygen ring that isn't particularly stable. You can see that that wants to go, right? So our question was, could we go to paracymene from 1,8-cineol instead of limonene? And is there any advantages associated with that? So my one slide from heterogeneous catalysis, the answer, I'll give the quick overview. The answer is yes. We can absolutely do it with 1,8-cineol, just a little bit of acidity in the support, does dehydration like falling off a log. And so you can get the same product from 1,8-cineol at the same reaction conditions, at the same reaction time and everything, because that reaction is so facile to remove water from it. So there's no advantage to having limonene over going to cineol, 1,8-cineol. So now you could go back to the biology folks and say, well, which is preferred option for the biology? Well, it turns out there's a very clear preferred one. And these were toxicity studies. And it turns out that limonene, which is a more hydrophobic molecule, so you could almost predict that this was going to be the case, has a much higher toxicity. So this is the same organism with a different, just a different different enzyme for either going to 1,8-cineol or going to limonene. And you can see you can go to much higher titers with 1,8-cineol because it's a less toxic molecule. So in this case, the right route to paracymene is actually through 1,8-cineol rather than limonene. Okay, well, that's all well and good. But now we're still back to this target dilemma question. And I always like to add target dilemma when commercially relevant is a goal. I mean, we can come up with any target if commercially relevant we don't care about, but somehow I feel constrained by commercial relevance. So what are we looking at? We can look at drop-in versus new molecule. Well, the issue with drop-in is we have impurity sensitivity. If I make the same molecule biologically that I make chemically, I have different impurities. Even if I'm 99% pure, that 1% impurity is different. And that can be a problem in polymerization. It's a moving price point. So here's the big problem, folks, for bio-based chemicals. If I'm going to do drop-in replacement, is a lot of the petrochemicals they've already capitalized away. Their capital has gone down to zero. And so they can lower the price to keep you out of the market if you're a bio-based chemical. That's the harsh reality. Okay. So new molecules. Well, the problem with new molecules is we don't have good structure function understanding for most molecules. It's pretty remarkable. We use these molecules, but we don't really know why they work lots of times. It's more we just found that they work. So we can't predict very well what structure we need to make biologically. Unfortunately, it's also not driven by the manufacturer of the chemical. It's driven by consumer demand, right? That's what they want, functionality. So the manufacturer is like, if I make this molecule, does anyone care, is a problem. And we have reaction pathway limitations. So we feel there's an all of the above answer to this, which is what we've coined bioprivileged molecules, which are biological intermediates that allow us to get to either drop-in replacements or novel molecules simply. And this is really important. It's not okay to make a biological molecule and have 4 synthesis steps after it to get to our molecule. We're talking, we make the biological molecule and in 1 or 2 steps, we can get to other molecules. Okay, so that's what we think is a way to leverage technology. So I'll give one example, and I'll go through this fairly quickly. There's a number of slides just to give some technical veracity underneath this, but I'll go through those pretty quickly. So we like this molecule, triacetic acid lactone. Not a molecule that anyone would make. It is a secondary metabolite. Generally, it's produced in plants, but you can take the pyrone synthase from this and drop it in human. Zhao had done this originally at Illinois and made decent titers of tau. We did some further work at Caltech or at Seabrook with it. Tau is interesting because you could do ring opening chemistry, end up with sorbic acid, which are a known molecule. In fact, all of these molecules are known molecules. So these would be drop-in replacements that we could all get to from that same starting molecule tau. Well, we got particularly interested in this molecule pogostone over here, which again is present in a plant called the patchouli. And I don't know if any of you have ever heard of patchouli oil, but patchouli oil goes back to the 1800s. And patchouli oil in India, they would rub it on cloth before they shipped their cloth to England. And it's because it repelled moths, is why they did this. It's also known to have antimicrobial activity, the pogostone molecule. And what's interesting here is if you look at that pyrrole pogostone and the one below it, dihydroacetic acid, they're essentially the same, but with just a different keto group hanging off that tau ring. And it's also got fungicidal bacteria. And so our question was, well, that's super cool. We know these exist, but if we're now going to get a differentiated molecule, what about all the other side chains you might make off of tau? What kind of efficacy would they have? So we made a library of those off that molecule. So this is another advantage in our view of bioprivileged molecules. We can use those to create molecular libraries. So this was a molecular library, small library, but library nonetheless. And really a lot of analogy to the pharma industry at this point, right? I mean, I'm not claiming we invented the wheel here. And here is pogostone is A, C is 1 carbon less, G is 1 carbon more. We did MIC testing on this, and the plus means that it was successful in killing off that organism. And sure enough, pogostone was pretty good across a range of different microorganisms. 1 carbon less was a little less effective. Interestingly enough, 1 carbon more was more effective. So here was a case where we could rapidly get to a novel molecule that could be uniquely accessed by biological coupled with chemistry. Another area we're interested, because I mentioned the moth repellency thing, we said, well, what about insecticidal activity? This is what we use largely are these pyrethrins on the side. Challenge with pyrethrins that they've now been around a lot of years. So we think of antimicrobial resistance. That's because microbes' life cycle is so short, they can evolve against that. Well, thank God, insects' gestation period's a little longer, so it takes them longer to evolve. However, they do evolve, and they're starting to evolve. Mosquitoes are starting to evolve resistance to these standard classes of pyrethrin compounds. So we were interested in, could we screen these molecules for insecticidal activity? You already know I wouldn't be presenting this if the answer wasn't interesting. We looked at it for both killing roaches, and it was quite effective as well as repellency. In fact, we had pogostone-like derivatives that had the same repellency properties as DEET. And I will announce a very clear conflict of interest here. We started a company in October 2021 dedicated to commercializing insecticides called Pyrone systems. Another quick problem, inhibitors. Corrosion inhibitors right now are largely inorganic materials. A lot of concerns they're toxic in the environment. So there's been a lot of work done on plant extracts. The challenge with plant extracts is they're very complex. Lots of times you don't know which molecule is active for it. And so we said we're going to adopt the same strategy of using tau and as our starting molecule, make a molecular library of molecules and test its corrosion efficiency. So I'm not going to go through that. It's just how it's done. Over here on the right is the organic corrosion inhibitor that's used, eutropin. And so 30% says it's a resistance that you're measuring to corrosion. So a higher number is good. If it's 0, it means you're not resistant. It's like just the acid is eating the iron away. What you can see is we have a number of these molecules that in fact have much higher corrosion resistance than the existing organic corrosion inhibitor. Now, on both this one and the insecticide, I want to be abundantly clear. The challenge with new products is very much like the challenge that you heard from Steve with SAF, or what are the standards? What are the requirements? And so you have to get through all the regulatory approval to get these new molecules to the market, which is not a trivial thing. Okay, so I hope I convinced you the bioprivileged molecules are at least an interesting paradigm with which to go at this. But now you can ask the logical question of, okay, how do we find the bioprivileged molecules? So we had a team that was looking at this problem, and the way we were looking at it was we are making great advancements in machine learning and being able to scan the literature. And there's decades of literature on molecules that have efficacy for different applications. So our thought was, if we data mine the literature, could we find chemical structures that could then be our candidates for bioprivileged molecules? And if we had reaction network computational analysis from that, we could say what were the molecules we could make if we had reaction operators that we could employ on those, what are in principle molecules we could make, and we could identify then bioprivileged molecules that we would use for molecular library synthesis, just like the example I showed with tau. And in fact, for this, the corrosion inhibitors that I showed you previously came out of this project, although admittedly, we already had a structure in mind that wasn't data mined to get through tau, and we had tau, but we were going to use that to try to close the loop back to say, from what we learned from tau, could we help inform the data mining? And we are also doing flame retardant polymers. So just computationally, what we were doing then was we were pulling these candidate molecules out of the literature. So this was a challenge in its own right? Because different people they don't use the chemically rigorous name sometimes for molecules, they use a popular name. So being able to find the name and correlating it with a chemical structure is a very non-trivial thing to do, but that's what we were going to do. And the idea was, if we could get those candidate molecules, we could put them in this reaction network analysis and essentially run that backwards and say, is there a molecule that would allow us with 1 or 2 synthesis steps to get to those candidate molecules? And that would be a bioprivileged molecule. It sounded like a great idea at the time. I will readily admit, we are challenged with making this to happen. And it turns out it's because that literature data mining is so difficult to do, because the chemical structure, you have a lot of isomers that have the same chemical structure, but have same chemical identifiers, same amount of carbon, same amount of hydrogen, same amount of oxygen, but they're totally different chemical structures. And so it's really hard to tie chemical content to the chemical structure. So this is still a work in progress. And I think still has possibilities, but it's going to take more work than we maybe thought. Okay. So I'm getting close. So here's what I would say. Developing bio-based chemicals. We need a target for, if we're going to do biotechnology to make a product, we need a target. Biology is sufficiently complex. We have to have a target. We can't just randomly walk through biology and manipulate stuff and see what we get. We have to have a clear target with which to do the design, build, test, learn cycle. We would like to argue that that target should provide us capabilities for both drop-in replacements and performance advantage. Why? Because performance advantage has higher value proposition. So if you can demonstrate it with that, you can go down the cost curve to go to a drop-in molecule, and then you would already have the infrastructure in place. So already you can start to see why is there value in having both. Admittedly, the initial market will be small, but it'll be higher value. We think along with that then, if you're going to do these novel materials, you got to be able to do molecular screening. So you got to be able to do that efficiently, at small scale, to get that to work. Now, bioprivileged molecules might not be the right answer, but I can tell you, we have to come up with a systematic strategy with which to go after bio-based chemicals. This idea that we're going to continue to just opportunistically find one. Yes, we will find a few that way, but it's going to be a long, meandering walk in the wilderness to get there. And that's just the reality. Okay, I promised the small policy piece. I'll just give a few policy pieces and then some future ideas. There is a little bit of help here. The USDA has this bio-preferred program, and this is important because it's supposed to give preference to products with bio content for federal procurement. And federal procurement is important because that's a very large consumer in the market. And so that's a really important program. I just have some other examples. There's an Iowa bio-based chemical production tax. So the way this works is, and it's specifically for if you're making a platform chemical that can be converted into other things, you are given a 5 cent per pound tax rebate. So for each pound you make, you get 5 cents of tax break on it. There's other things that aren't helping us in the bio-based product area. There's been a big battle going on at the EPA about the CO2 policy. And right now, EPA treats CO2 from biomass identically to CO2 from petrochemicals, which means CO2 from ethanol production is every bit as bad as CO2 from burning crude oil. It's treated exactly the same by EPA. So there's been a lot of effort to try to differentiate biogenic CO2 versus to no luck yet. There was an interesting development last September, this executive order out of the White House in advancing biotechnology and biomanufacturing. We'll see what happens. These are always mandates without dollars, so it'll be interesting to see what happens there. Future needs. So this will be my last one. Leveraging existing infrastructure is tremendously important. So even though everyone likes to talk about the high price value of chemicals, we still need to leverage existing infrastructure. And Steve talked about this as well in that. I mean, this is why fuel solutions that use existing refining capacity can move much faster than brand new capital infrastructure because it can utilize existing. It's going to be the same in the chemical space. How do we leverage existing infrastructure? Product scale-up knowledge is still horribly lacking in this. Fermentation scale-up, we do in a 96 well titer plate, then we do shake flasks, then we do 1 liter fermenters, then we do 100 liter fermenters, then we do 1,000 liter fermenters, and then ultimately do a 50,000 liter fermenter. Well, in the petrochemical area, there's lab scale, there's pilot scale, and there's commercial. So we're competing against, we have to go across 5 to 6 length scales in biology. We go through 2 length scales in the petrochemical industry to bring new things in. Big, big problem. I won't talk too much. I don't want to, downstream processing is going to be enormous. Separations, this is really underappreciated in the space. And there's still this need for these larger demonstration units, which don't currently exist in the US. My last final comment, which is going to be my most provocative and is going to annoy the most people out here, is this concept that we're going to use bio-based chemicals to subsidize fuels. I will tell you, in my opinion, 100% nonsense. Because now ultimately it could be true in our nirvana state that we co-produce fuels. But imagine if I'm going to drop a greenfield site that has new fuel technology processing and new chemical processing all at the same time, no one is going to absorb that technical risk. I can assure you this is the case. Having worked at Shell, we will not drop 2 distinctly different new processes in a new greenfield site. Too much risk. No way. So how do we get from here to there? We need to find ways to, with our existing infrastructure, to start to get bio-based products produced and mainstreamed, and then that technology is proven that we can then tie in with biofuels in the future. Okay. Again, I'm sure there'll be people that don't appreciate my viewpoint there. Just want to finish with thanks to the funding agencies and key people that helped in this work.
Okay, we've had an information-rich morning, so we're going to take about, we'll be back at 11:30, and then we're going to have a little discussion about what was presented to you this morning. So there's coffee still in the back and some fruit, it looks like. Bathrooms again, out the hall, straight back that way to the left where the big red wall is. See you at 11:30. Okay, we're going to move on here now. We have one more presentation before lunch. This one is going to come to us remotely. So next we have Mark Shmorhun, who is the technology manager for the U.S. Department of Energy, Biology, Techniques, and Biology. Let me start again. I can say this, I can. The U.S. Department of Energy, Bioenergy, and Technologies Office. Mark is a technology manager there, and he collaborates with biotechnology companies and national laboratories to develop and mature mid-stage biofuels, bioproducts, and biopower R&D with an emphasis on chemical process development, plant engineering, and design. Mark attended Drexel University, where he received his BS in chemical engineering and MS in materials engineering. Mark earned his PhD in macromolecular science and engineering from Case Western Reserve University and has an MBA from the Raymond A. Mason School of Business at the College of William and Mary. So coming to you via Zoom. We're ready back there, Zoomers?
Can you hear me okay? Could I get an audio check, please, to make sure I'm being heard?
I can hear you.
Awesome.
For you.
Yes, good morning, everybody, or I think it's morning there still. Hi, I'm coming to you from Rockville, Maryland. I'm Mark. I'm with the Bioenergy Technologies office. I apologize I couldn't be there in person today. I was on the road from the middle of last week until yesterday and just needed to get home. So thank you for allowing me to present remotely. So I'm going to talk about DOE's Bioenergy Technology Office and what we do. I think you'll find that a lot of what I have to say really dovetails nicely with the presentations from Steve and Brent earlier this morning, and perhaps even a little bit of overlap. So let's see if we can get slides to advance here. All right, so I'm going to talk a little bit about EERE and DOE and our decarbonization strategy in transportation, industry, and agriculture. Spend a little time on scaling process technologies or technology in general, and then some key research initiatives out of our program office. So guiding principles as the department, DOE's energy efficiency and renewable energy segment, we're here to accelerate research, development, and demonstration of innovative technologies to help transition our country to a clean economy by no later than 2050. So if you look at our programmatic priorities, they include decarbonizing the electric grid, decarbonizing across all transportation modes. Obviously, SAF falls in there. Decarbonizing energy-intensive industries, reducing the carbon footprint of buildings, and then enabling a net zero agricultural sector. So obviously we don't work in a vacuum. A lot of what we do is cross-agency, for example, with DOT and FAA and USDA, et cetera. So along the way, we want to ensure that we have the greatest impact. So that is, we have a high level of focus on environmental justice and equity, diversity in STEM, the workforce development, and empowering state and local partnerships. Okay, so if I was given time to have one slide, this would be it. And then I'll cover this and then we'll tunnel down a little more deeply as we go through this. So the top line here, I realize this is a little busy. The transportation sector in the United States accounts for 12.6% of our GHG emissions. I'm sorry, 37% of GHG emissions. And passenger cars, air, marine, and rail account for 13% of that. Ag is 9%, and the industry sector is about 20%, or I'm sorry, overall chemicals is about 5.5%, and that's 19% of the industrial sector. So if you look left, so we're here to develop and demonstrate technologies that cost effectively decarbonize hard to electrify modes of transportation. I would say hard to electrify is very relevant here. So as Steve mentioned earlier today, by 2050, we still anticipate a great deal of demand for liquid hydrocarbon fuels for commercial aviation. We'll see the same in marine, relying on liquid fuels, the same thing perhaps with long road, on-road trucking that goes long distances and rail. So we're here to continue R&D to enable competitive fuels across multiple conversion pathways And as we fund projects these days, we're looking for a greater than 70% emissions reduction. My group within BETO is responsible for also standing up topics and investing in the GHG emissions of the Gen 1 corn ethanol industry. And then we have a specific goal of standing up and getting into operation 4 to 5 SAF demonstration scale facilities by 2030. So a key strategy, if you look right, for improving the economic viability of biofuels is bioproducts. I agree with Brent entirely that no one's going to stand up a complicated fuels and products plant coming out of the gate, but product-oriented facilities that have higher value, that have an easier shot at being profitable at small scale will probably lead the way and help grow and mature the supply chains that are necessary for larger volume, lower margin, high volume fuels. So we also invest in products. Our goal is to develop 10 new performance advantage materials by 2025. We have a goal of having 10 commercial bioproducts by the end of this decade, leading to 1 million metric tons of CO2 emission reduction. And by 2050, roughly 2 orders of magnitude greater than that. All right, so just quickly, in the United States, this is pre-COVID, 2019, transportation accounts for 34% of GHG emissions, and a good deal of that is from aviation, medium and heavy duty vehicles, and light duty trucks. And then you see as well, a good chunk of this pie is the industrial sector. And if you look to the right, the industrial sector breaks down, as you can see it, cement, food products, iron and steel, chemicals, refining. So, and then on top of it all, you have ag, which contributes to about 9% of our GHG emissions. So again, our office is in EERE, Energy Efficiency Renewable Energy. BETO falls in the transportation segment of there, thus our focus on the reduction of emissions from these hard to electrify transportation areas. All right, so if you look further, a little deeper, the current fuel types by use, as you look at transportation, liquid fuels are on the left-hand side. So jet, diesel, and gasoline, and those are the approximate distributions. And then you can see the fuel use by mode. So light duty vehicles on top of heavy duty vehicles, off-road, aviation, et cetera. So if you look at the consensus on scenarios by 2050, there will be a reduction in demand for liquid fuel on light duty vehicles as that segment gets electrified. And then you have growth in aviation and modest growth in the other sectors. So the point of the chart in the middle, as you look at that 2050 scenario, we firmly believe, and we have investigated this thoroughly, is that there are significant and ample sources of renewable biomass and other renewable materials in this country that can achieve a good deal, not 100%, but a good deal of that liquid transportation demand. And so you can see how they stack up. And I believe Steve had a slide a little earlier today that showed these various feedstocks and their potential. Hopefully our data aligns, we'll see. So we're here to develop and demonstrate those technologies, again, in areas that are hard to electrify. And so we're going to continue to work on 70% GHG reduction, minimum 70% GHG reduction platforms. We are, again, investing in the first generation ethanol industry because that is emerging as an important feedstock for the production of aviation fuel. And then, again, 4 to 5 demo scale biorefineries by the end of this decade. All right. So the Sustainable Aviation Fuel Grand Challenge, which I've been working on for a few years, has set some goals. So this is government-wide. It began a number of years ago with a memorandum of understanding developed between DOE, USDA, and DOT. And we set out some goals that we needed to hit a minimum of 50% reduction in GHG emissions. We wanted to hit the goal of 100% aviation fuel demand from renewable resources by 2050, with 3 billion gallons by 2030. So this is a lofty goal, and it's going to require doubling of current domestic capacity year over year. So our grand challenge hopes to accelerate RD&D through increasing focus on interagency collaboration, leveraging resources, catalyzing industry actions, coordinating government, state, and local policy, and of course, enhancing international leadership. There's a lot going on across the globe in terms of SAF and growing SAF supply. The chart on the upper right is the similar one, although to what Steve showed, his was much cleaner. So I'd refer you to that chart. So we released our roadmap in September of 2022. There will be a significant update to that roadmap later this year. So please stay tuned. In the next couple of months, we'll probably have a website up and running that tracks our progress on the SAF Grand Challenge. Alrighty. This is a what if kind of slide, but the point of this slide is to show you that feedstocks are there, they're available, and they can stand up to meet our fuels challenge. And you can see, for example, I'm just going to pick on one line, seed oils. I'll take the first line in this chart, seed oils that could feed into a HEFA process, which is a similar refinery, similar to you all or familiar to you all as a refinery technology that in the United States, we predict about 9 million dry tons per year of these seed oils could be put into production, yielding, somewhere around 2 billion gallons per year of a combination of jet, diesel, and gasoline cuts. So if you look at it overall, we figure that there is the potential to produce about 60 billion gallons per year of liquid fuels from renewable feedstocks. And I should have prefaced this conversation by saying my email address will be at the bottom of this deck. You'll have it, and please reach out to me if you have any questions about any of these details. So bio-based chemicals and materials are going to be super important. A little redundant, Brent mentioned this earlier, but yes, you can make direct replacements that are chemically identical to what's coming out of petro at lower GHG emissions. You have the opportunity, however, to make performance advantage materials that have superior properties and new uses. We also are keenly interested in those platforms and the resulting intermediate chemicals and products that can be made from those. And a good chunk of our portfolio is invested in the discovery and development of pathways to produce these bio-based chemicals and materials. So the chart on the upper left, the little graph, is to demonstrate that we do believe that if we focused on jet as opposed to a blend of jet and chemicals, that we can get there. So in a jet-focused case, let's say we put our resources into SAF, there would be naturally some spin-off of co-products in materials, renewable chemicals. But we can have a balanced case where we're looking at the production of that 35 billion gallons of SAF with the potential to produce billions of pounds of renewable chemicals. So renewable chemicals are important. We're investing in them. And again, to recap, we're targeting 10 new materials by 2025 and looking at the introduction at commercial scale by 2030. And obviously, we don't introduce the commercial scale. We help enable that through our investments in de-risking of those technologies. All right, so plastics innovation has become an important thrust for our program office and other program offices within DOE. We have a DOE-wide comprehensive program to deliver solutions to reduce plastic waste and reduce the emissions associated with plastic production. We're looking to address end-of-life fate for about 90% of plastics, which are mostly going to landfill today, looking at reducing energy savings relative to production of plastics from virgin materials, reducing, achieving 75% carbon utilization from waste plastics, cost competitive, recyclable by design, bio-based plastics, and reducing GHG emissions. So BETO focuses on plastics and biorecycling, leveraging our know-how in the design of organisms and other platform technologies. So to be very clear, this is a cross-cut activity across DOE that involves the Office of Science, BETO within energy efficiency, renewable energy, our AMO, the Advanced Manufacturing Group within EERE, ARPA-E, and of course, fossil energy and carbon management. So this is a wide multidisciplinary effort within DOE. And last but not least is agricultural pillar within BETO. We have a group that focuses on renewable carbon resources, and ag is a component of that. Obviously, I think no surprise to anybody here. You grow biomass. If you convert that to a fuel, that fuel will still emit CO2, but you close the cycle because that CO2 will get recycled in the production of new biomass. Very different time scale from petroleum, which releases CO2, and it's kind of somewhat irreversible. So ag is a source and a sink for greenhouse gas emissions. It's key that as we look at this to decarbonizing our overall industry. And we are developing tools and strategies and ecosystem services that produce biofuels with lower carbon intensity by tackling agricultural challenges, such as maximizing CO2 sequestration, developing climate smart ag practices, producing energy on site from animal waste, for example, small scale anaerobic digestion systems, and developing wastewater treatment strategies that also produce bioenergy feedstocks. And an example of that would be the conversion of anaerobic sludge from wastewater treatment to biocrudes. So we are engaged here as well. All right. So the area I'm most familiar with is scaling technology. That's where I make my living. We invest in applied R&D through large-scale demonstrations. So we do, across our portfolio, very fundamental work at low TRLs 2 and 3 through TRL 6 or 7. And if you look at TRL 7, this is usually called the Valley of Death, where building, funding, and constructing a demonstration scale plant is really pretty difficult. These are not, you can't really raise debt to build a demo scale plant, let's say that produces 1 to 10 million gallons of aviation fuel. That plant will not make money. But it's really necessary to demonstrate and de-risk technology at scale. So if you look across our portfolio, we are active through TRL 7, through demo scale plants, and partnering with private entities to help de-risk those technologies and put equity into those projects with the hope that these technologies then have legs in the commercial sector. Pursuant to that, last week, we were very delighted to announce $118 million in competitively awarded projects. There are 17 projects across the United States that'll boost production of biofuels and support Biden's agenda for decarbonization and climate. The selected projects include pre-pilots, pilots, and demo projects that scale to produce fuel and bioproducts. These products do align with the first ever U.S. National Blueprint for Transportation Decarbonization, which is a multi-agency framework. There will be a link in this deck if you'd like to look at it. And I'm not going to go into these awards. There's 17 projects. I have a link here for a table. They range from a modest $500,000 for feasibility studies for first generation ethanol plants to reduce their carbon intensity, to an $80 million project, well, an $80 million DOE investment that will be factored up from there by an entity in Georgia that's looking to develop a demonstration scale alcohol to jet facility. So in this deck, there will be a link, or you can go on the BIDO website to see that list of projects. State of technology. I realize I need to talk to Csonka more often because my slide's out of date. Sorry about that, Steve. So you saw the earlier one, but I guess my takeaway from this is that, we're on a pathway. A lot is happening. BIDO has 3-4 projects in its portfolio that are building demonstration scale facilities. There's examples around the planet of these things happening. When you see numbers like this and you see this development and this investment, you start gaining confidence in our 3 billion gallon per year target by 2050. So good for us. All right. In support of that, we need diversity of biomass across the United States. Our program office with the national labs actively maps where these resources can be grown, where they're available. So we're going to need about 650 million tons of biomass to make that 35 billion gallons of SAF. So I use biomass generically. That also includes other renewable resources such as municipal solid waste. No single resource will get us there. We need different pathways, we need different supply chains and different feedstocks. So we invest in these tools and we are out there and happy to work with entities that are looking to site facilities and need some guidance. Scale up is not easy. It takes a very long time. The point of this slide is to show you that, from 2005, doing strain development on organisms that would enable gas-phase fermentation of waste gases, it's a pathway. So, in this case, probably a 15-year time scale where you're going from very small scale work at the bench to what we call commercial scale reactor sizes. And that little sentence down at the bottom talking about alcohol to jet is a similar story. The LanzaTech technology licensed from PNNL, that catalyst development work began in 2010. And today, DOE and BIDO are working with LanzaJet to put steel in the ground for the first demonstration scale facility that should be operating sometime in 2024. So you're not going to do this stuff overnight. From bench to commercial scale takes a decade plus. All right, so I'm going to bring us home some key research initiatives. Brent mentioned this earlier. The Agile Biofoundry is looking at how to accelerate biomanufacturing. We have Bottle around looking at what we do with plastics, both recycling and bottoms up the design of new plastics. And then lots of work, I haven't really touched on this, is looking at CO2 and other waste gases and the conversion of those into renewable fuels. Just quickly to give you a sense of our budget, I'll ask you to look at this table, go right. We asked for a lot of money, but we got a good amount. So the FY23 enacted, our budget is $280 million. And SDI, my program, has about 92 million to do scale up and demonstration of facilities, renewable carbon resources at 80 million, conversion at 100, and our data group around 9.5 million. So we are emphasizing sustainable aviation fuel through our D&D, looking at sustainable ag and investing in renewable chemicals. Honestly, we wish we had more money. We had a lot of demand for the scale up, around investments in pilot and demonstration scale facilities, and we funded what we could. And just to note, not a complaint, the bipartisan infrastructure law really has no funds for biofuel demonstrations, which in our view is a bit of a weakness, but it is what it is. All right. So this is my penultimate slide. So just to give you a sense, here's our ecosystem. You have plants that are consuming CO2 and sunlight. They're making biomass. And we are focused across the spectrum from pretreatment of that biomass to sugars, to various other pathways, biochemical and thermochemical conversion to make fuels and power and bioproducts. And we're also looking at the conversion of CO2, CO, and other waste gases to fuel. And of course, integral to all this is CO2 sequestration. So just to give you a sense, our program is super diverse across multiple pathways, and with a real focus on risk reduction and demonstration of technologies that will help reduce emissions and get us to where we want to be by 2050. So with that, I will say thank you. And I hope I did it justice. I'm a chemical engineer, I'm a scale-up guy, and I'm trying to cover all programs. So if I messed up, please shout out. I'll get you to an expert in our program office. So with that, I'll stop sharing. Thank you very much.
Thanks, Mark. With that, we're going to take a break for lunch. We'll reconvene at 1 o'clock.